My voice and the screen is good. I will start my talk. Okay.
Yes, make it a full screen.
Okay, I have full screen and play the slides. And today the title of my talk is Swarm of Microflying Robots in the World, and that's also the title of our recent paper published in Science Robotics. And I think that's why we are sitting together in today's webinar and exchange our ideas. And we are very honored that this paper is also selected as a cover page paper in that May issue of Science Robotics. And now I'm going to talk some details of our this work. Okay. First of all, I want to introduce some research background. The reason why we want to doing fully autonomous aerobatic swarm is that, as we observed in industrial and academic, until the publication of this work, there was no swarm system that can operate in fully unknown environments without any external localization devices and also without any external human operations. For example, we can see from the no matter the DARPA offset program and the CETC swarm system from USA and China, the swarm robot system relies heavily on GPS or external ground station to control the drone scenario robots, and also in the research field in academia, we can see from the previous works in swarm published before our paper in Science Robotics, they propose autonomous swarm, but they have only very limited autonomy, which means they can only do some simple finish some simple tasks such as follow the walls and explore indoor environment. And other works such as from this work in published recently in TRO, people are doing the swarm coordination and planning, but also this work heavily rely on a motion capture system to localize the drones and rely on a ground station to compute all the trajectories. And all this computation are done in offline. And so based on the observations and the basic motivation, I summarize some research challenges that we have to solve them first and then move forward to our the ultimate goal to make a miniature size, autonomous and collaborative area swarm system. And these four challenges, I name them as lightweight, which means we have to build a very tight drone platform that has limited size, weight, power, and it can do agile autonomous flight in even very complex environment. The navigation functionality should be very robust to deal with many disturbances such as wind and other human disturbance. And also this whole system should work all by itself. It should be a fully autonomous system. And after we finish all these challenges, I think we should, I hope we can finally make some swarm systems such as shown in the red videos. I quote them from some scientific movies. And also, by the way, I think that's also the point that robotics fascinated me a lot. They have some long-term fascinating scientific imagination as a long-term goal, and it should also have many step-by-step solid technology accumulation that can help us chasing this dream. Okay, and to this end, we have to firstly deal with a basic system consist of some many basic problems that how to make a single drone that can fly with full autonomy. We name this diagram as a perception action closed loop, which means the drone should use this sensing capabilities such as camera and other sensors to collect information from the real world and compute the right pose of itself at real time, which is named localization. And it should understand the environment, at least where the obstacle is and where the free space that it can fly. That's called mapping. And based on localization and mapping, the drone have to do the planning, which generates a safe flight path for it to avoid any possible collisions and navigate it to the final target. And then the controller will execute the flight path perfectly and let the drone can localize to stabilize itself during the flight. After all this stuff done, we have built an autonomous drone such as shown in the right-hand side figure. And this drone is built in our lab in Zhejiang University, which has a stereo camera and also use the initial measurement unit inside the flight controller to do the localization and mapping. And all the functionality included the localization, mapping, planning, control are done in the onboard computer in real time. And after we build this single drone, we want to research a step forward towards the coordination, and then we can build a swarm system. Okay, as I just introduced the basic idea of the perception action closed loop, we can see from these 3 videos I just selected from our recent publications. We can see from the first video, the drone is flying with full autonomy, but it's also flying very aggressively. So it has very high requirements on the precise control and the real-time high altitude and aggressive motion planning. So it's a very hard mathematical problem to be solved in real time. And in the second video, we are showing that a drone is flying with full autonomy at a very high speed. The speed is up to 10 meters per second in a totally GPS-denied environment, which is in underground garage where the environment obstacles are previously unknown to the drone, and it has to detect all the obstacles and plan a safe flight path in real time. And certainly, this video shows that a drone equipped with only vision sensors to fly without any external localization and devices in previous indoor and outdoor experiments. Okay, and I summarize some more technology difficulty we have to face towards the next step, swarm. Because current work we have successfully shows the application of single drone navigating in static environments. But if we want to extend it to swarm, we have to deal with 2 challenges. That the first is we have to plan safe surface in a fully dynamic environment. Because we have multiple robots, they will interact with each other during the flight, even in a static environment, and also the environment may be a dynamic one. So we have to extend our plan algorithm, also the sensing algorithm in a fully dynamic previous unknown environment. And also we have to make our algorithm that can support more than one drone at the same time. Okay. To this end, I want to firstly introduce some of our recent works in about the and autonomous navigation in dynamic environments. For example, as we can see from this video, and this work is published at AAAS 2021 and is one of the best application paper finalists. And in this work, our drone is only equipped with a stereo vision sensor, and we will classify the obstacles as static one and a dynamic one. And after we do the obstacle classification, we will also have a module that will track all the moving obstacles and predict their future motion. And based on the sensing of the static and dynamic environments, we will build 2 maps. And then we propose a 2-layered motion planner that can guarantee the safety against both static and dynamic obstacles. A simple system diagram is shown in this figure. And also based on the safe obstacle avoidance in a dynamic environment, we want to add more functionality to our drone. We want this drone can follow moving people of course, in an uncooperative way, which means June has no information, has no communication and coordinated control with the tracked target. So our June has to keep a proper distance to the target, which means they can not be too far from the target, because in this way it may lose the target and fail the tracking. But also it cannot be too close to the target because it may be dangerous to the human. So we propose a new algorithm, namely elastic tracking. We model the tracking distance constraints like as an invisible spring between the target and the June, because it has a stretchable flexibility according to the situation to keep them in a proper distance. But this is just an imagination and just a motivation how to mathematically solve this problem. It's a planning. It's a concrete planning program. So we write down this tracking trade optimization, and we can find that we have many constraints, such as boundary condition constraints. The June has to always start from an initial pose it now has, and it should be this June should always has a collision avoidance constraint to avoid any possible collision, and also the visibility guarantee, which means June, since we have limited field of view of the vision, so we have to keep that our June the target is always in the FOV of the robot. And finally, we have the distance keeping constraint I just introduced as which is modeled as an invisible spring. So we put them all together and propose a new customized optimization solver to quickly generate a safe flight trajectory, which is represented as piecewise polynomial. Okay, and recently we also extend the tracking application further. We want to do the autonomous landing, which is also named as perching for birds. And we also use this word perching in our aerial robot to let it quickly can land on a moving inclined surface. So based on the tracking program, you can see from the previous slide, we have a kind of complicated mathematical program. And now we want it not only can follow the target, but also can land on this moving target. So we have more constraints and the program become even more difficult. But fortunately, since we have our customized resolver, which is a method named Minko and published in this year's attribute transaction robotics, we can our trajectory generator can support any kinds of user-defined analytical constraints for the June, and also no matter in static and dynamic environments, our trajectory generator can safely generate a dynamic feasible curve for the June to flight within several milliseconds. So we successfully do the error approaching. Also, based on all these recent research progress and of course also the previous single joint navigation technology in static environments, we think it's time to push the boundary of the autonomous swarm. So in last year, we built a kind of a scientific swarm system, which composed of many more. I think here many means more than 10 miniature swarm aerial robot platform, and with each one can do all the autonomous navigation with only its limited onboard sensing capability. Okay, first of all, I want to introduce some of the hardware design. As you can see from these figures, our June has a very limited size. Its tip-to-tip size of only 8 centimeters. And the total weight of the June without the battery is within 200 grams. And with the battery, its total weight is within is about 300 grams. And also, for such a lightweight platform, we cannot afford heavy and accurate sensors such as LiDAR. So our June only equipped with very simple and cheap stereo camera. It's from Intel company. And for the computation, although our drone has a very limited size, we want it can do many complicated tasks such as the formation flight, the collision avoidance, and many other high-level tasks such as target following. So it should have a sufficient computation resources to do all the calculation in real time. So here we select the NVIDIA Xavier NX computer for the onboard computer. And other component includes the UWB sensor, which can measure the drone to drone distance during the flight without any ground station. It's a non-ground station version of the UWB sensing. And also, since we cannot find a proper flight control unit, we customize flight control unit ourselves. So nowadays we have made a very small flight controller chip, and based on the open source, and also we are known flight controller framework PX4, and we customize the software and the hardware design based on PX4 and made the chip. Now we have this very small chip which can support the autonomous flight of our drone. And based on this system, based on this hardware design, we also design a new fully decentralized swarm software architecture. The core idea of our swarm architecture is that we want our swarm system can be very flexible. Here, flexible means all the drone, each of the drone in the swarm system will do all the calculation related to its own flight all by itself. So we have no centralized brain to coordinate and communicate with each other. Each of the drone do its own calculation. So even during the flight, one drone crash or two drone crash, remains of the swarm will continue its flight. And during the flight, also you can command some drone to join the group, and they will reform a new swarm and do the same flight task, which is as defined before the flight mission. Okay, and here's a snapshot of our system in experiment, and then we'll components by components to introduce some key methodology used in this paper. Here, firstly, I want to show the resources consumed during the flight of our swarm system. We can see from these figures. Also, all these figures are from our paper, so you can check the details in the paper in Sun Robotics main issue. And you can see from statics that the localization part always takes the most computing resources, because since our drone has only the very poor kind of poor sensing capability, which composed of only very cheap and low accuracy IMU, and also the very short-sighted stereo cameras. It has to we have to put many computing resources to do the visual inertial localization. And based on the visual inertial localization system, we also have another positioning algorithm which fuses the VLO and the UWB measurements to calculate the relative position and relative translation and rotation between each two drone in the swarm. So only in this way, we can guarantee that the swarm in the flight can form a predefined shape. Otherwise, since the VL system always have a portrait, no matter how accurate your odometry is, then after very long time flight, your formation will always divert. So the UWB measurements and the fusion algorithm is also very important. And besides the localization system, we have also put a lot of computing resources to the mapping and coordinated planning. And the main, although we consume most of the computing resources in localization and mapping, the core novelty or the contribution of our paper is a planning algorithm. Here we integrate many of our previous research results on trajectory generation and pathfinding in this one. And also we put some new ideas to it to make the system can plan can plan very robustly, even in very complicated environments. So the basic idea here is that we want that our system can be a user-defined block by block system, which means you can define the objective of this flight, such as you want the drone can flight as smooth as possible, because if the drone has many sudden stop and accelerate, it will consume a lot of energy. So we want it can fly very smoothly. This objective is always modeled as maximizing smoothness of the flight trajectory. And also, we sometimes want the drone can fly as fast as possible, which is the minimization of the flight duration, or so-called the minimizing the flight time. And of course, we have to avoid obstacles. So it's an obstacle avoidance constraint, and also the dynamic feasibility constraint. Here, dynamic feasibility means our drone has a physical limitations on its performance in real-world experiments, such as the thrust generated by each propeller has a upper bound. So you cannot generate a trajectory that requires the drone to fly very fast. It cannot fly that fast. So it's a kind of physical limit. And also it has many other inner layer physical limits, such as the body rate, which means the maximum angular velocity of the drone is always a very important concern during the planning. And besides the body rate, and also besides the body rate and the thrust, and also we have to constrain the acceleration, we have to constrain the velocity, we have to constrain many other physical parameters to so that makes them can be really executed by our hardware platform. So we put all these objectives and all these constraints together, and based on our previous work Miko, and also I have to explain that Miko is only for one drone, and here we extend Miko to a multi-drone scenario. So based on our planning algorithm, with this framework, we can translate the objective plus constraint program to an unconstrained mathematical optimization program. And also we derive a way to easily calculate the gradients of each term of the objective towards the parameters to be optimized. Here, the parameters means since we use a piecewise polynomial to represent the flight trajectory, so the parameters of the planning is just the coefficients of the polynomial and also the time duration. And here is the mathematical description of our algorithm. I think that may be kind of complicated if you are not familiar with trajectory generation or not familiar with mobile robot planning. But trust me, it's already a simplified version of our algorithm. So if you want to know a very detail of the algorithm, you have to check this paper, and you will find there are so many equations, mathematical proof. Okay, one word to summarize is that we translate the planning requirements to a unconstrained mathematical optimization program, and we have a customized solver which let us can solve it very efficiently. Here, efficiently means we can generate very difficult trajectories with respect to all the physical limits in just 1 or 3 milliseconds. Okay, apart from the optimization itself, we also put some technologies also called tricks to make our planning algorithm, to make our planning system more robust against many challenge and unstructured environment. For example, is a topological planning. Here, the topology in planning means if there is an obstacle in front of you, you can go around it, right? You can go around it both in the left side and in the right side. And in both sides, it's okay for you to go to the target behind the obstacle. But during the flight, if our drone, because it's always doing high frequency planning during the flight, it will generate trajectories in 10 or 20 hertz during the flight. So 1 second it will do 20 times planning. And if the drone choose to go obstacle in the right hand side and in next planning is then decide to go in the right hand side, then the drone will shift and you will find that for a single juice navigation, it will oscillate during the flight, and for a swarm, it will tend to fail the obstacle avoidance mission. So here we add the topological planning module to make our system can always choose the better topology. Here, the better topology means you can go either the right side or the left side, but we always choose which side is better according to some predefined rules. So in this way, our drone can consistently choose one side to go around obstacles. It will have more stable and predictable flight performance in this way. And we integrate all this together. And first, we test our algorithm in simulation. And here in simulation, you can see there are many different colors which indicate different map sensed by different drone during the flight. And all the red curves are the flight trajectories generated by each drone to avoid any possible collisions. Here, the collisions is not only to avoid for the static environments for the obstacle, but also for other drones. Okay, and here is another video showing the performance of our algorithm. Since I think the sufficient and necessary condition for multiple drones to avoid collisions is that they will not appear in the same place at the same time. So the trajectory generation, the planning for a swarm means we have to optimize the shape of the trajectory and also the time of the moving at the same time. So here we show the performance of optimize the time and or not optimize the time using our same planning framework. And of course, if we optimize the time, which means the drone can appear at the same place. That's a very that can be easy to understand, but they appear at the same place, not at the same time. So in this way, even there is a very narrow gate for the drone to pass through. This such as this showing this video. There's some very narrow corridors. Our drone can automatically generate the safe trajectories to go through the narrow door one by one. Okay, and testing the plan algorithms in our system, we also do some benchmark against some newly proposed swarm planning algorithm published in TRO or other prestigious robotics journal. And from this statistics, we can see, especially for the computing time and the minimum clearance, which indicates the guaranteed safety for the algorithm, our method has a kind of superiority against the benchmark algorithms. And also, here are some more tests showing that even we have many different kind of objective and constraints to formulate a kind of complicated mathematical program, we can always safely generate the right solution. We check the minimal spacing between each drones during the flight, and also check the maximum velocity and other constraints. And we found that our algorithm can always respect to these constraints, no matter where they come from. And besides the planning, some other some other key capabilities are very, very important. For example, I have just told the relative localization functionality come from the sensor fusion from visual initial and initial measurement and also URB distance measurement. Without this sensor fusion, we can imagine that each drone will has its own post drift during the flight. And after here is an experiment to show this phenomenon. After about 20 or 30 meters flight, our formation will diverge quickly. But with the fusing of the URB, we can maintain a good formation even in a very cluttered environment. And finally, we can show some real-world experiment to verify the capability of our algorithm and also our hardware. And firstly, here is an experiment. I know many of you have already seen these videos, possibly many times, but I want to show it more. We test our system in bamboo forest in Anji, which is a very beautiful city in Zhejiang province. And here is a very difficult experiment because inside the bamboo forest, the passing space for the drone is very, very limited. I think for me, I piloted drones more than 10 years. I cannot safely pilot the drone to pass through this difficult environment. Okay, as you can see from this video, at the bottom line of this video, it's a dense 3D map building, which is built during the flight. Because we have 10 drones, each of the drone in the swarm has its own vision to detect some obstacles and build a map. And after we accumulate all the information from each of the drone, we can have a dense map which indicates the terrain information and also obstacle distribution of the flight. And the second environment shows the formation keeping capability of our algorithm here. Also, I want to emphasize the flexibility of our algorithm, which means we can keep a formation in clear space. You can see from this video, they have a two-line formation, right? But when they encounter some obstacles, the drones in the swarm will quickly go around the obstacle. They will deform the formation and keep the safe flight put the safe flight at the first place, and after each of them go around obstacles and return to the safe space, they will quickly reform the desired formation. Okay, and these two experiments are also clearly shown in our paper. For the first experiment, we want to emphasize that some part of the testing scenario is very difficult. It has very limited size for the drone to pass. And for the second test, we want to show the deform and reform capability of the swarm formation, which means our algorithm can quickly select the best way to keep the balance of safety and also the user-defined objectives such as the formation keeping. And the third experiment is target following. Instead of the previous experiment, I have shown that the drone follow one drone following people moving around in indoor environment. Here we are showing that we have a 4 drone team. Is a small size swarm system, and 4 drones will continuously follow the moving person. And even one drone's vision is occluded by some unknown environment, other drones will tell it that the target is moving towards which direction. So the one which is occluded will have the information to continue its task. I think that's good evidence of what a swarm can do, why a swarm can do much more better than just an addition of some single 1 or 2 or 3 drones, just simply add them together. And finally, the last experiment is a robustness test. We call it intensive reciprocal avoidance test. Here we let 10 drones to select randomly the target in a circle. And during the flight, my student, Mr. Zhou Xing, who is also the first author of this paper, he will continuously walk through this flight area and add some new obstacles, and also we will interact with some of the drones to make it to add some more difficulties to the test. And we can see from this video, our algorithm can always generate safe flight trajectories even in such a dynamic and challenging environment, because each drone has to avoid collisions with others, and also avoid possible collision with the moving newly added obstacles, and also until it consumes all the power and receives the commands to land. Okay, here are the results of these two experiments showing the successful application in such user-defined high-level swarm applications, such as target following and the continuous position swapping. And finally, I want to show a video of a simulation platform we call it Swarm Playground. And here I want to show this simulation because it's part of the open source results of our paper, and we have released this simulation environment and also the core mathematical planning algorithm together in our group's GitHub. If you are interested in multi-drone planning and also interested in maybe the trajectory generation or drone simulation, you can check the QR code and have more information about this package. We provide some interface for the human to send his command to the drone, and also to a single drone, and also to a team. And here also we provide some functionality that you can add some moving obstacles, such as many moving cars to test dynamic obstacle avoidance capability. And also we implement a very simple version of the formation keeping algorithm. So in the simulation, you can try it yourself. Okay, and finally, here is my group. Now I'm leading a small group consisting of around 20 students and research assistants working in Zhejiang University, and also Huzhou Institute of Zhejiang University, which is a wonderful place to conduct cutting-edge research. So if you want to know more information about us, you can scan the QR code and go through our website and have a look of our open source project, and also the published and the preprint papers. Okay, thanks.